What if I told you the silicon everyone has been fighting to control? The chip that built Nvidia's entire kingdom, the one governments are scrambling to restrict? The engine under the hood of the entire AI revolution might be built on a fundamentally wrong approach, not slower, not weaker. Wrong, as in a completely different physical principle, that a Chinese research team just sidestepped entirely, because while the planet has been fixated on electrons, shoving tiny charges through ever-shrinking transistors, a lab in Shanghai fabricated a chip that barely uses electricity to compute at all. It uses light, real photons, beams of light performing the actual calculations, and they are claiming this photonic chip can execute certain AI workloads up to 1,000 times faster than Nvidia's most powerful graphics processors, while sipping a fraction of the energy and producing almost no heat. 1,000 times, not 1,000%. 1,000 times. Now, before you let that number carry you away, it comes with heavy qualifiers. And I'm going to give you every single one of them straight, because the genuine story underneath is far more fascinating than the clickbait. By the time this video ends, you will understand precisely how a chip computes with light, why that matters so profoundly for artificial intelligence, exactly where the 1000x claim holds up and where it crumbles, and why this might represent one of the most significant shifts in computing in generations happening, yet again, in a place the rest of the world was not watching carefully enough. Let us dive straight. To grasp why a light-powered chip is such a massive deal, you first have to understand the brick wall that every electronic chip on the planet is crashing into. Every computer you have ever touched operates by shunting electrons around. Microscopic electrical charges stream through tiny switches called transistors, flicking on and off billions of times per second. That dance of electricity is what we label computing. It has served us brilliantly for 7 decades, but it carries 2 fundamental problems that are intensifying every single year, and no amount of clever engineering can fully escape them. The first enemy is heat. When you drive electricity through a material, that material pushes back, and resistance generates heat. The more muscular the chip, the more electrons you force through it, the hotter it becomes. Modern AI data centers now spend a staggering portion of their total electricity bill not on actual computation, but on cooling, just fighting to stop the chips from incinerating themselves. We have explored this on the channel before. It is why diamond cooling became a billion-dollar battlefield. Heat is the silent tax on everything. The second enemy is raw energy consumption. Training a single large AI model can devour as much electricity as hundreds of households consume in an entire year. As artificial intelligence swells, its power hunger is becoming genuinely unsustainable. Corporations are now openly discussing building dedicated nuclear reactors simply to feed their server farms. That is not a figure of speech. That is a concrete plan, because electrons are ravenous. So here's the question. A small group of researchers started asking years ago, what if we abandoned electrons for computation? What if we used something that does not resist, does not heat up in the same way, and propagates at the fastest speed the laws of physics permit? What if we computed with light itself? This is the segment that sounds like pure science fiction, so let me anchor it in reality, because the central idea is genuinely beautiful. Recall the last time light passed through a glass of water and bent or separated into a rainbow, or 2 ripples on a pond crossed and merged into a larger wave. Light naturally interacts. It bends, it combines, it interferes with itself in precise, predictable, thoroughly mathematical patterns. And here is the breakthrough insight that demanded decades to transform into hardware. Those natural interactions are mathematics. When 2 beams of light superimpose, the universe is, in a very real sense, executing a calculation instantaneously at light speed using 0 transistors. A photonic chip is engineered to exploit exactly that phenomenon. Instead of wires ferrying electrons, it contains microscopic channels, waveguides, that steer beams of light. By splitting those beams, phase shifting them, and recombining them in meticulously designed geometries, the chip performs the exact category of mathematical operations that sit at the very heart of artificial intelligence. The multiplication of enormous matrices of numbers over and over again, that constitutes the vast majority of what training and running an AI actually is. And it turns out light is astonishingly gifted at that specific flavor of mathematics. Here's the analogy I find most useful. Traditional electronic computing resembles dispatching thousands of messengers through a jammed subway network. They collide, they produce heat, they queue in tunnels, they burn energy at every step. Photonic computing is like transmitting those identical messages as laser pulses through open air. No congestion, no friction. No resistive heating, just information propagating at the one velocity nothing in the cosmos can surpass. That is the dream researchers have chased for decades. The reason it remained a fantasy for so long is not the physics, it is the manufacturing. And that is precisely the barrier a Chinese institute now claims to have shattered. The chip at the center of this entire story originates from an institute called ChipX, collaborating with a company named Turing Quantum based in Shanghai. And what elevates their announcement above 20 years of photonic computing promises is not a laboratory curiosity, it is a factory. Here's what they constructed. A 6-inch wafer composed of a substance called thin-film lithium niobate. That material selection is the entire secret, so lock onto it. Onto that wafer, they integrated more than 1,000 optical components, the minuscule light splitters, phase shifters, and channels that execute the computation. Over 1,000 of them packed onto a single chip, all cooperating with photons. Why does lithium niobate carry such weight? Because it possesses a nearly magical property. When light traverses it, you can precisely manipulate that light, its phase, its amplitude, its timing, and you can perform that manipulation incredibly rapidly, with very little of the optical signal leaking away. It remains stable at room temperature, which means no exotic, wallet-draining cryogenic cooling for sculpting light on a chip. It sits close to an ideal material. The obstacle was always that processing it at volume, producing real wafers crowded with these fragile structures without fatal defects, was brutally difficult. Many laboratories could fabricate one, almost nobody could manufacture them reliably at industrial scale. ChipX asserts it has solved exactly that problem. In June, the institute launched what it describes as China's inaugural pilot production line for these thin-film lithium niobate photonic wafers, boasting a capacity of roughly 12,000 6-inch wafers annually, with each wafer yielding approximately 350 chips. Now, in absolute numbers, 12,000 wafers is microscopic compared to a giant silicon foundry that churns out hundreds of thousands. But for this specific bleeding-edge category of photonic chip, it represents a genuine industrial beachhead, the dividing line between a science experiment and the embryonic stage of a real supply chain. And the developers claim these chips are already deployed in practical settings, in domains like aerospace and finance. So what about that headline figure, the 1000x? Here is where I must be completely candid with you, because this is precisely the sort of claim that lands channels in hot water when they skip the fine print. The 1,000 times faster than Nvidia figure is genuine in the sense that it was explicitly asserted by the developers and reported by credible outlets such as the South China Morning Post. But it arrives with 3 critical pieces of context that the breathless headlines omit, and you deserve all 3. First, and most crucially, that speed applies to specific, narrowly defined tasks, not general-purpose computation. A photonic chip is not a socket-compatible replacement for your computer processor, and it is not a drop-in substitute for an Nvidia GPU across the board. It is ferociously fast at one particular category of mathematics, the optical interference calculations it is physically constructed to perform. For those specific workloads, the acceleration is genuine and staggering. Ask it to execute something outside that tight lane and the advantage evaporates. As one set of researchers phrased it, these chips can outperform GPUs by orders of magnitude, but only within tightly constrained domains. To borrow an analogy, it resembles comparing a top-fueled dragster to a family sedan. On a perfectly straight quarter-mile strip, the dragster is unbelievably, jaw-droppingly faster, but you cannot drive it to the supermarket. You cannot merge onto the freeway, and it cannot navigate corners. The 1000x is a drag strip number. Nvidia's chips are the sedan you can pilot anywhere. Both realities are simultaneously true. Second, there exists a separate but connected breakthrough worth knowing because it strengthens the narrative, not weakens it. Researchers at Shanghai Jiao Tong University and Tsinghua University, in a paper published in the prestigious journal Science, demonstrated a fully optical chip named LightGen, constructed with over 2 million photonic neurons that executed image and video generation tasks more than 100 times faster and more efficiently than a leading Nvidia GPU. So this is not a solitary laboratory making an extravagant claim. Multiple serious Chinese research groups are independently demonstrating that light-based chips can pulverize GPUs at narrow AI functions. The pattern is authentic, even where any individual number is debatable. Third, the honest caveats: the technology still confronts genuine hurdles. Yields remain modest. The long-duration reliability of these chips under sustained heavy load is not yet fully established, and the precise methodology behind that 1000x measurement stays somewhat opaque. This is frontier, early-phase technology. It is not poised to replace every Nvidia chip in every data center next year. So here's the equitable summary, the one you will not receive from either the hype merchants or the dismissive skeptics. China has not rendered Nvidia obsolete, but it has demonstrated in physical silicon rolling off an actual pilot line that for the specific mathematics upon which AI leans most heavily, there exists a fundamentally different and dramatically more efficient method to compute, and China is currently the party scaling it toward genuine production. Here is the dimension of this story that I find genuinely absorbing, and it connects directly to everything else unfolding in this technology race. When the planet's largest tech powers contemplated the future of radical new computing, most of them, particularly in the West, placed enormous bets on a different path: superconducting quantum computers. Immensely potent in theory, but burdened with a brutal catch. They must be chilled to nearly absolute zero, colder than interstellar space inside colossal, delicate, astronomically expensive refrigeration apparatus. It is a moonshot that demands extraordinary infrastructure. China placed a different wager. It poured serious resources to room temperature photonic computing, chips that utilize light and function at normal ambient conditions, no exotic cryogenics necessary. And here's why that bet is so ingenious and so consistent with the pattern we repeatedly observe. Photonic chips, unlike the most advanced electronic chips, can be fabricated using older, more mature manufacturing processes, the kind that do not demand the single most sophisticated, most heavily restricted chip-making instruments on the planet. Do you perceive the maneuver identical to the GPU-free supercomputer? Identical to the novel approach to chip design we recently examined, being walled off from the bleeding edge of electronic and semiconductor fabrication pushed China to invest massively in an entirely different paradigm of computing, one where the export restrictions lose most of their teeth. Light does not require a 2-nanometer transistor. Photonic computing occupies a lane where the controls lose much of their grip. The wall once again failed to halt the water. It simply altered the direction it surged, and this time it surged toward light. Let me pull the lens back, because it is easy to lose the forest for the trees here. No serious observer is declaring silicon deceased or Nvidia finished. Electronic chips are versatile, mature, and woven into the fabric of everything. They are not vanishing for an extremely long time. The plausible future is not light replacing electronics. It is light joining them. Picture a data center where the flexible, general-purpose workloads execute on traditional silicon, but the specific, brutal, repetitive mathematics at the core of AI gets offloaded to photonic chips that perform it 100 or 1,000 times more efficiently. A hybrid architecture capturing the best of both worlds, and that future matters enormously for one reason above all others: energy. If even a fraction of the world's exploding AI workload can be shifted onto chips that compute with photons, generating less waste heat, drawing a fraction of the power, it could meaningfully bend the curve on AI's terrifying energy appetite. That is not solely a speed narrative, it is a sustainability narrative. It might represent the difference between an AI future that is viable and one that gets strangled by its own electricity bills. And the strategic dimension is equally vast. For years, the entire framework of this technology contest assumed the battlefield was electronic semiconductors: who can fabricate the smallest transistor, who commands the finest lithography scanner. Photonic computing potentially reframes the entire competition. It is a different battlefield, governed by different rules, and China has quietly constructed one of the most formidable early positions upon it. Regardless of whether any single 1000x headline withstands scrutiny, that is the development the rest of the planet ought to be monitoring. Here's my candid assessment. I believe the most intelligent way to hold this story is with two ideas simultaneously refusing to collapse into either convenient simplification. On one flank, the voices shouting that China just made Nvidia obsolete with a magic light chip are sprinting far beyond the evidence. The 1000x is a narrow drag strip figure, yields are constrained, and this is nascent technology with genuine unanswered questions. Anyone selling you that narrative is selling hype, but on the opposite flank, the people rolling their eyes and dismissing it as merely a niche laboratory toy, ignore it, are committing the larger error. And it is the identical error observers keep repeating in this race, because underneath the inflated headline rests something genuinely substantive. Multiple serious Chinese teams publishing in journals like Science, fabricating actual chips on an actual pilot production line, proving that light-based computing can demolish the world's finest GPUs at exactly the category of mathematics AI requires most urgently. That is not nothing. That is the early outline of a different future. What strikes me most forcefully is how familiar the pattern has grown. Severed from the most advanced electronic chip fabrication, China did not simply try harder to catch up on the identical road. It invested in a road that loops around the obstruction, entirely light instead of electrons, room temperature instead of near absolute zero, mature fabrication nodes instead of forbidden machines. Over and over, the constraint becomes the catalyst. I genuinely no longer believe that is luck. I believe it is the defining strategy of this entire era, and we are observing it unfold in time. So here's my question for you, and I truly want your honest answer. Do you believe the future of AI computing belongs to light, these photonic chips that run cool and sip power? Or will electronic chips like Nvidia's remain on top because they can handle everything even if they run scorching hot and thirsty? Is light the authentic future, or merely a brilliant specialist that will never escape its narrow lane? Drop your unfiltered take in the comments. I read every single one, and I suspect this one is going to ignite a genuine debate if you want to keep tracking this story, the breakthroughs, the workarounds, the technologies the rest of the world underestimates until they suddenly cannot. Subscribe to Empire of Tech and smash the notification bell. Chips, light, energy, supercomputers, the entire foundation of modern technology is being rewritten right now, and we break it all down before the mainstream catches up. Thanks for watching. I will see you in the next video.